Reimagining hydrogen storage, a theoretical approach using centrifugal force and gas layering. Introduction. Hydrogen has long been regarded as a promising clean energy source, with the potential to revolutionize transportation, industry, and energy storage. Its abundance and high energy density make it an attractive alternative to fossil fuels. However, despite its many advantages, hydrogen faces a significant challenge: storage. Currently, hydrogen is stored under high pressure or at extremely low temperatures, requiring expensive materials and complex infrastructure. This exposition explores a bold, unconventional approach to hydrogen storage, using centrifugal force and gas layering to potentially overcome these challenges. Understanding the hydrogen storage challenge. Today, compressed hydrogen is stored in carbon fiber tanks, but this method comes with limitations: high costs associated with carbon fiber and manufacturing processes, leakage risks, as hydrogen molecules are the smallest and can seep through many materials, storage volume inefficiencies, as hydrogen must be stored at extremely high pressures, 700 bar or more, or low temperatures, minus 253 degrees Celsius. For hydrogen to become a mainstream energy solution, we need an alternative storage method that is both cost-effective and efficient, and this is where the proposed approach begins. Theoretical concept: centrifugal force and gas layering. The idea behind this unconventional storage solution is to use centrifugal force to separate gases by their density, creating a natural barrier to contain hydrogen. Centrifugal force naturally causes heavier gases, such as argon or xenon, to be pushed outward, while lighter gases, like hydrogen, remain at the center. The goal is to layer heavier gases around hydrogen, effectively creating a gas-based container that doesn't rely on solid materials like carbon fiber. This method could potentially reduce costs by eliminating the need for expensive materials and making hydrogen storage simpler and more scalable. Simulation and initial results. Physics simulations were conducted to explore how centrifugal force could segregate gases and allow hydrogen to remain at the center. The simulation showed that under centrifugal force, lighter gases, hydrogen, indeed stay concentrated at the center, while heavier gases, argon, move outward. This initial result suggests that centrifugal force could act as a self-sustaining barrier, keeping hydrogen contained without the need for traditional tanks. The potential application of this approach is significant, as it could simplify the storage process and lead to cost savings in hydrogen infrastructure. This content is brought to you by Bobby Giggs. Promote your brand here and reach a wide audience across platforms like YouTube, Instagram, and Facebook. Follow the links in the description to get started. Reimagining hydrogen storage, a theoretical approach using centrifugal force and gas layering. Advantages of the proposed method. There are several advantages to using centrifugal force and gas layering for hydrogen storage. Cost reduction. Eliminates the need for expensive carbon fiber tanks and high-pressure storage systems. Simplicity. The use of gas layering as a containment system simplifies the storage process and makes it scalable. Flexibility. This method could be applied to different industries, such as automotive, energy storage, and even industrial applications. By focusing on natural physical forces rather than complex engineering solutions, this technique offers a path toward more affordable and widely accessible hydrogen storage. Challenges and considerations. Despite the promising theoretical results, there are several challenges to consider. Stability. How stable is the gas layering over time, particularly when there are pressure or temperature fluctuations? Alternative gases. Which gases are best suited for creating stable layers around hydrogen, and how can we ensure they won't leak or interact negatively with hydrogen? Scalability. Can this approach be scaled to real-world applications, such as large hydrogen storage facilities or vehicles? Further research and testing are needed to address these challenges and refine the concept. Implications for the future of hydrogen energy. If successful, this new storage technique could revolutionize the way hydrogen is stored, distributed, and used. Lower costs. With cheaper and more efficient storage, hydrogen could become a dominant energy source, competing directly with fossil fuels. Sustainable energy transition. The ability to store and distribute hydrogen more efficiently could accelerate the global transition to clean energy, reducing dependence on oil and gas. Global infrastructure. This method could simplify the development of hydrogen infrastructure. Hydrogen stations, pipelines, and transport systems could be built more quickly and affordably. Hydrogen could replace fossil fuels in numerous sectors, from electric vehicles to industrial processes and even in power generation. This makes the exploration of new storage methods more crucial than ever. Conclusion: hydrogen holds incredible promise as a clean energy solution, but its storage remains a critical challenge. By exploring unconventional methods like centrifugal force and gas layering, we could revolutionize the way hydrogen is stored and distributed. While challenges remain, the theoretical results of this approach are promising and warrant further investigation. The future of hydrogen depends on innovative ideas and the willingness to challenge existing paradigms. As we continue to push the boundaries of what's possible, breakthroughs like this could pave the way for a clean, sustainable, and efficient energy future.